Hello lovelies, in this video we're going to look at all the content that you need for your Edexcel GCSE Physics Paper 2, and this is to a grade 9 standard. Now once you've gone through this video, make notes, rewound, pause, watch things over again as you need to. What I want you to do is to go up to the website and have a look at our predicted paper, have a look at the walkthroughs of our predicted papers, and then you can feel really confident that you've done as much revision as you can for potentially your last exam ever.
I want to start off here by looking at prefixes. These are used throughout physics through all of the topics to describe the order of magnitude of a quantity. And when we're doing calculations, we need to make sure that we use the SI unit. So if they give you something such as milliamps, we need to convert it to amps. So we need to know that tera means times 10 to the 12. It's a very big number. Giga is times 10 to the 9, mega is times 10 to the 6, kilo is times 10 to the 3, centi, like centimetre, is times 10 to the minus 2, milli is times 10 to the minus 3, micro, which is this little Greek symbol, a bit like a curly U, is times 10 to the minus 6, and nano is times 10 to the minus 9. And you'll see here that I've highlighted out the centi one. And the reason I did that is I just want you to imagine, if that wasn't there, notice the pattern with the numbers. They're going down by 3 each time. This is a really easy way to remember these. So all you need to do is remember the order of these prefixes, and then you can work out the order of magnitude. So an example of how we might use this in practice is if we're told that we have 40 milliamps, for example, but we need to calculate something using that value, we will need to rewrite it in just amps. So in place of the M for milli, we write times 10 to the minus 3. So 40 milliamps is equal to 40 times 10 to the minus 3 amps. Please do make sure that you get these memorized. We need to know about energy stores and systems. A system is an object or a group of objects. We might refer to a closed system, which is a system when energy can't escape or enter the system. So closed systems are particularly important because in a closed system, the total energy remains constant. However, the energy may be transferred between its stores. So getting on to energy stores, we need to know the following ones. We need to know about kinetic energy, gravitational potential energy, elastic potential energy, internal or thermal energy, chemical, nuclear, magnetic and electrostatic energy. So kinetic energy is the energy of a moving object. An example of this is a moving car. Gravitational potential energy is the energy an object has when it's raised above the ground. So an example of something with gravitational potential energy is a book on a shelf. Elastic potential energy is the energy an elastic object, for example a spring, has when it's stretched or compressed. Internal or thermal energy is the total kinetic and potential energies of all the particles within an object. An example of this is a hot cup of tea. Then we've got chemical energy. This is the energy stored in chemical bonds. An example of this is a battery or some food. Nuclear energy is the energy stored in the nucleus of an atom. An example of something that has this nuclear energy is the uranium fuel in a nuclear reactor. Then we've got magnetic energy. This is the energy that a magnetic object has when it is near to a magnetic field. An example of this is a fridge magnet. Then we've got electrostatic energy, and this is the energy that a charged object has when it is held near to another charged object. This can be seen in Van de Graaff generators. Energy can be transferred between different stores using 4 different methods. The first is heating. So energy will be transferred from one object to another if there's a difference in temperature, a temperature gradient, and it will travel from the hottest to the coolest. Radiation is another way we can transfer energy, and in this case the energy is transferred as a wave. An example of this is infrared radiation from the sun. Then we've got electrical work. This is the energy transferred by the flow of charge due to a potential difference. Finally, we have mechanical work. This is the energy transferred due to a force moving an object through a distance or changing its shape. So an example of an energy transfer is a book falling from a shelf. Initially, that book on its shelf had a gravitational energy store. However, that was transferred mechanically by the force of gravity to the kinetic energy store. We need to be able to say different energy transfers dependent on a scenario given to us in an exam. A force does work on an object when the force causes the object to move through a distance. The work done by a force on an object is given by work done equals force times by distance, where work done is measured in joules, force is measured in newtons, and distance is measured in meters. Of course, as always, we could use a little cheeky triangle here if you struggle with the algebra. If not, I would always recommend that you just rearrange this using the algebra that you've learnt in maths, but it's always good to have something up your sleeve in case you get stuck. If you did use a triangle, I would just pop a W on the top for work done and force times distance on the bottom. Now, we need to know that 1 joule is equal to 1 Newton metre. And this is because 1 joule of work is done when a force of 1 Newton causes a displacement of 1 metre. It's also really important that we know that work done against friction will result in a temperature increase. And this is why if you rub your hands together, they start to get warm, because you've done work against friction. Kinetic energy is the energy of a moving object. So the equation for this is kinetic energy equals half times mass times velocity squared. Or the simple equation of this is EK equals a half mv squared. So the units of kinetic energy is joules, the units of mass is kilograms, and the unit for velocity is meters per second. Gravitational potential energy is the energy gained by an object raised above ground level. To calculate the gravitational potential energy, we multiply together the mass with the gravitational field strength and the height. If we do this using symbols, then that's Eg is equal to m times by g, the gravitational field strength, times by the height. Now looking at units, gravitational potential energy is measured in joules, just like all of the energies are. Mass is measured in kilograms. Gravitational field strength is measured in newtons per kilogram. And height is measured in meters. Power is the rate at which energy is transferred. We can find the power in one of 2 ways. The first way we can use is that power equals energy transferred divided by time, or P equals E over T. Now remember, power is measured in watts, energy transferred is measured in joules, and time is measured in seconds. Alternatively, we could say that power equals work done over time. In this case, that's P equals W over T. Power is still measured in watts, time is still measured in seconds, and work done is measured in joules. We should know that an energy transfer of 1 joule per second is the same as a power of 1 watt. And we should also be able to compare different systems. If, for example, I was picking up a box and lifting it up to a certain height, the quicker I do that, the more power I have. The law of conservation of energy states that energy can be transferred usefully, stored, or dissipated, but it cannot be created or destroyed. And this is a really key fact in physics that we will use all the time. So when energy is dissipated, it is transferred to less useful stores. For example, if we have a light bulb, we take that electrical energy store that's inputted and it gets transferred to light energy, which is useful, but also thermal energy as it heats up. Now this thermal energy is the wasted energy or the dissipated energy. It's important that we know that all energy will eventually be transferred to the thermal store of the surroundings. In the exam, we might be asked how we can reduce unwanted energy transfers. There's 2 examples that they expect you to know. Firstly, we can lubricate it, and secondly, we can add thermal insulation. Those are 2 ways that we can reduce unwanted energy transfers. However, always have a think to the context of the question. For example, lubrication might be useful if we're talking about things rubbing over each other, because that will reduce the friction and therefore that thermal energy transfer that wouldn't be useful. However, I'm sure you can imagine that that wouldn't be useful for every example. So try and always think about the context and think, how can you reduce that unwanted energy transfer? The energy efficiency of an energy transfer can be calculated using one of 2 equations. Efficiency is equal to the useful output energy transfer divided by the total input energy transfer. So useful output over the total input. Alternatively, if we're given powers instead, we can say that the efficiency is equal to the useful power output divided by the total power input. So very similar idea. It's that useful output divided by the total input. Now both of these equations as they stand will give our answer as a decimal. Now in the exam you might be asked to give your answer as a decimal or as a percentage. If we needed to get the efficiency as a percentage, all we do is we use these equations, but then we multiply our answer through by 100. If we ever needed to increase the efficiency, we need to increase the amount of useful energy transfer. Therefore, we need to minimise the amount of energy dissipated and wasted. The way that we could do this is things like streamlining, things like lubrication, try and stop frictions within the system, which could of course lead to energy transfers into less useful forms of energy. In physics, we learn about scalar and vector quantities. A scalar is a quantity which has magnitude only, so it only has a size associated with it, whereas a vector has both that magnitude but also direction. So in physics, we might often see vectors represented using an arrow, and the size or length of that arrow gives us an idea of the size of the quantity, and the direction it's pointing tells us the direction of it. Now at GCSE, of course, we learn about so many different things. Now, I've got this little table here just to summarise whether certain things you've learnt about are scalar and vector. So we need to know that speed is a scalar, whereas velocity is a vector. Distance is a scalar, whereas displacement is a vector. Time and energy are both scalar quantities as well, because they just have a size associated with them, not a direction. Whereas acceleration, force and momentum, all of these things we will learn more about, are all examples of vectors. All forces are either contact forces or non-contact forces. Contact forces are experienced when objects are physically touching. Some examples of this include friction, where things are rubbing against each other, air resistance, where the air is in contact with you, tension, and also the normal contact force. And there's loads of other ones too. Non-contact forces, on the other hand, though, involve objects that are not physically touching. They're physically separated, and yet they're still experiencing a force between them. So some examples of this include magnetic forces. If you've ever held 2 magnets together, you'll be able to feel, even though they're not touching them, pulling together or pushing apart, even though there's no physical contact. As well as this, we have electrostatic forces and also gravitational forces. Now, don't forget that force, whether we're talking about contact forces or non-contact forces, are vector quantities. So they always have the magnitude, but also the direction. Lots of forces can act on an object. However, we can replace all of these different forces with just a single force called the resultant force. Now, the resultant force is just a single force that has the same effect as all of the original forces acting together. Let's have a look at what that means. So if we had a 4 Newton force and we added another 4 Newton force in the same direction to it, there would be a resultant force equal to 8 newtons in that same direction. However, if we had a 6 Newton force, and it was encountering another 6 Newton force, but in the opposing direction, because force is a vector, we could say that this is actually minus 6 newtons. What's going to happen then is these two forces are going to cancel each other out. And so actually the resultant force is equal to 0. Make sure that you can do these yourself as well, because they could ask very similar questions in the exam. A single force acting at an angle can be resolved into two components that act at right angles to each other. So this diagram that I have here shows that. This diagonal force, which is acting of course at this angle here, can be split into this horizontal component and this vertical component. Now these two components have the same effect as the original single force. Now when we draw these diagrams, it is very important that we make sure that we draw these arrows in the tip to tail formation. So this horizontal one that we have here, tip is here, and then we put the vertical component that makes that overall resultant force so that the tail of it, the end of it, is touching the tip of the other. Now remember that this resultant force here is not an additional force that adds up with the other two. Instead, that is the overall force of those horizontal and vertical components. Now, we can actually do this the other way around too. We can work out the resultant of two forces that are at right angle to each other. We can do this by drawing a scale diagram. So we can get a ruler, work out what scale we want to use, and draw the horizontal component. So say if we had something that was, 6 newtons, we could draw something that's 6 centimetres long perhaps. Then if we had a vertical component that was 8 newtons long, we could do something that's 8 centimetres long in that vertical direction at the end of our 6 Newton force. Then we can draw a line to connect the two, which would be this pink line that I have here, measure this line and use the scale to determine the resultant force. So in this case, if we were using that scale, then we could measure this pink line and we'd see that it's 10 centimetres long. So therefore it is 10 newtons. And that is how we can use scale diagrams to work out resultant forces. We also need to make sure that we can draw some free body diagrams. Now, a free body diagram is a diagram that we use to describe situations where there are several forces acting on an object. So here we have an example of a free body diagram on an accelerating car. Here we can see there's 4 different forces acting on the car. There's the weight which acts down, the normal contact force acting upwards, the resistance due to friction and air resistance going in the opposite direction to its motion, and the thrust going forward. Now here, if we look at these forces, the up and the down forces are balanced. There's no resultant force in the up and down direction. However, we can see that the thrust arrow is bigger than the resistance arrow. Now that means that we have a resultant force in the forward direction. Now if all of these forces in all directions were balanced, then there would be no resultant force. And that means that the object would be stationary, or if it was already in motion, it would continue at a constant speed. A lever consists of 3 things: a pivot, an effort, and a load. However, these can all be arranged in different ways. For example, in some scissors, we have the effort, which is our force that we push down on the handles. Pivot is in the middle, and the load is at the end on those blades. Wheelbarrows, on the other hand, have the pivot, followed by the load, which would be the weight of our contents of our wheelbarrow, and then the effort, which is our force of our hands lifting up that wheelbarrow. Now, levers can act as force multipliers. They allow us to lift heavier loads than the effort force would normally allow, so they're really, really useful. Now, longer levers increase the force exerted on a load. And a typical example of this is using longer spanners compared to short ones to turn a nut. It's just easier. Another example would be using a wheelbarrow with a longer handle compared to a shorter handle. This is also going to increase the force exerted on the load, making it easier to lift a heavier load. Now, an object can rotate if a force or a system of forces is exerted on it, and we call the turning effect of a force the moment of a force. Now, we can calculate the size of the moment using this equation here. Moment of a force equals force times by distance. Now, in this case, the distance that we're talking about is the perpendicular distance from the pivot to the line of action of the force. Okay, so make sure that you've got it at right angles to that force. Now, the moment is measured in Newton meters, force is measured in newtons, and the distance is measured in meters. If an object is balanced, it is in equilibrium. So in that case, the total anti-clockwise moment about a pivot is equal to the total clockwise moment about a pivot. Now, in a question like this, if you had to do some calculations, make sure you work out which forces will be making it turn in a clockwise or an anti-clockwise direction, and then work out the moments of all of the clockwise moments, all of the anti-clockwise moments, then add all the anti-clockwise moments and set them equal to the sum of all of the clockwise moments. Okay, so that's a really, really important rule we need to know. But it's all about things being balanced again, exactly like the seesaw, like you see here. If you imagined it balanced, it's because the anti-clockwise moments about that pivot would be equal to the clockwise moments about the pivot. A gear is a wheel with a toothed edge, like you can see in these diagrams. Now, the teeth of one gear is able to connect to the teeth of another gear, and therefore as one gear turns around an axle, the other will also turn. Now, it's important that we know that connected gears, like you can see in this diagram here, will rotate in opposite directions. As you can see here, if one of them is rotating in an anti-clockwise direction, the other one will rotate in the clockwise direction. So make sure you know that key fact as to what a gear is and how it works. Frictional forces can cause surfaces to heat up. This can result in an unwanted energy transfer. To reduce this unwanted energy transfer, we can reduce the friction between the two surfaces. We can reduce unwanted energy transfers using lubrication. The atom is made up of 3 different types of particle. So we have protons, which are positively charged particles found within the central nucleus of the atom. Then we also have neutrons, which are also found inside the nucleus of the atom. Neutrons, however, have no charge. Now we might see this referred to as being neutral. Now that third particle found within an atom is the electron. Now electrons are negatively charged particles, and we don't find them in the nucleus this time, we find them in shells which orbit the nucleus. So you can see all this in our little diagram here, and we have to get very used to these diagrams and being able to label them accurately. In the electricity topic, we really do need to know the following electrical components. We need to be able to draw them and recognise them. So let's start off with the switch. We can see it open and closed. We know that a cell is 2 little parallel lines, one's bigger than the other, and a battery is several of these cells. Could be 2, could be more than 2. That's what makes up a battery, several cells. Then we have the lamp, which is a circle with a cross through it. A fuse, which is a rectangle with a line going all the way through it. A voltmeter is a circle with a V in it. And of course, we need to know that a voltmeter is used to measure voltage. An ammeter is used to measure current, and its circuit symbol is a circle with an A in it. A for ammeter. A thermistor is a rectangle with a tick through it. It's really important that we recognise that this rectangle with no line through it is a resistor. So different variations of these rectangles are going to be different types of resistors. So an LDR is a rectangle with 2 lines going towards the rectangle. You may see it with a circle around it, but you may also see it without that circle. And this is a light-dependent resistor. And that's why the arrows go towards it, because it depends on the light. So the light's shining on it. And it's a rectangle because it's a resistor. Then just a plain old resistor is simply a rectangle. A variable resistor is a rectangle with an arrow going diagonally through it. And a diode, which is a component which only lets current flow in one direction, is a triangle pointing in one direction with a line on the end of it. And sometimes this may have a circle around it, sometimes it may not, but they both represent a diode. And finally, we have an LED, or light-emitting diode. This is just the same symbol that we had for a diode, so this triangle with a line on the end of it. But this time, because it's emitting light, we're going to point two arrows away from the diode to show it's a light-emitting diode. So circuits can be connected in two ways. Of course, we have our series circuit where there's a single loop, and then we have our parallel circuits too. Now, it's important that we know a few facts about series circuits and parallel circuits. So in a series circuit, we should know that the current is the same in each component. Now, this comes down to the fact that current is the flow of charge. Imagine you've got cars driving around one loop. You're going to have the same amount of cars just driving through the whole loop, aren't you? They're not got anywhere else to go. So current is the same in each component. However, the total potential difference is shared between the components. And the reason for this is the fact that potential difference is actually the work done per unit charge. It's an energy, and so that energy is going to get shared as it goes through each of these components. Now, total resistance, on the other hand, is the sum of the resistance of each component. So we need to know that if we saw this example, for instance, the total resistance would be the resistance of bulb 1 plus the resistance of bulb 2. If we were to look at parallel circuits though, because we've got these different loops, again, if we think of those cars moving along it, when it gets to the little junction, there's two options for where the cars or the current goes. So the current will split between the different loops. Potential difference, however, is the same in each component. And the potential difference is the work done per charge, and each of those charges are just each going through one component. So it's exactly the same for every one of them, regardless of which route they took. Total resistance, however, in the parallel circuit is a little bit different. It's actually less than the resistance of the smallest resistor in the circuit. We don't, however, have to do any calculations for the parallel circuits at GCSE, just the series circuit. Why does adding resistors in series increase the total resistance? Well, this is just simply the fact that the current has more resistors to pass through. However, when we ask the question of why does adding resistors in parallel decrease the total resistance, it's a little bit more complicated. So the parallel loops are going to add an additional path for the current to flow through. And so more current can flow in total, even when the potential difference remains the same. Again, if we think of cars, for instance, this really makes a lot of sense. If another route opened up, then suddenly the cars and the traffic is going to flow much more freely, and therefore, just like the current, that flow will increase. And this is why adding additional paths for that current to flow through is actually going to decrease the resistance, leading to more current flowing. When charge flows in a circuit, we should know that work is done. Now we can calculate the amount of energy transferred by electrical work using the equation that energy transferred equals power times time. We can use the symbols here, E equals P times T. If we're using our standard SI units here, energy transferred will be measured in joules, which is a capital J, power is measured in watts, which is a capital W, and time will be measured in seconds, which is an S. As is the case with most equations in physics, we can write this in a triangle if you're not very confident with your math skills. To do this, we just put the P times T on the bottom. Remember, the bit with the times always goes on the bottom of a triangle, and an E on the top. Then, for whatever it is that you want to find, just cover it up with your finger and then use the triangle to get your rearranged equation. For example, power P equals energy over time. Here I've included a little top tip, and this applies to any equation, not just this one. We might need to convert minutes to seconds. We need to know that we do this by multiplying the minutes by 60. Alternatively, they might give you the time in hours instead. And again, in all likelihood, we're going to need to convert this into seconds. We do this by multiplying by 60 to get it into minutes, and then by 60 again. So multiplying by 3,600 converts hours to seconds so that we can use it in this equation. Now, it's not uncommon in physics, if the question's about an electrical appliance, that energy may be measured in kilowatt hours. Now, if this ever did happen, then we can use this exact same equation, however using slightly different units. The energy transferred is now measured in kilowatt hours. To be consistent with this, the power would be measured in kilowatts. And then finally, the time would be measured in hours. The amount of energy transferred can also be calculated using charge flow Q and potential difference V. Energy transferred equals charge flow times by potential difference, or using the symbols E equals Q times V. In this case, the energy transferred is measured in joules, which is a J, charge is measured in coulombs, which is a capital C, and potential difference is measured in volts, which is a capital V. If you are someone who struggles with your maths, we can just learn this triangle with the E on the top and the Q times the V on the bottom to help us with the rearranging side of this. Remember to use the triangle, cover up whatever it is that you need to find. Remember that the line means divide and the times mean times, and then you should be able to work out anything you need using that triangle if you're stuck. An electrical current is the rate of flow of electrical charge, and by electrical charge we could be talking about electrons or ions. We need to know the following equation for this. We need to know that charge flow is equal to the current times by the time. It can often be helpful to use this as the symbol equation just because it's quicker to write. In this equation, we represent charge flow with a Q, current with an I, and time with a T. So we can say that Q equals I times T. Now it's important that we know that charge flow is measured in coulombs, current is measured in amperes or amps, and time is measured in seconds. So if we ever have a time given to us in hours or minutes, we do need to convert it to seconds. Now, of course, everybody's math skills is slightly different. Some people struggle with rearranging this equation, and some people prefer to use the triangles. Now, all I care about is you getting all of the marks in the exam. I do not care how you get it at all, okay? Some teachers can be a bit snooty about triangles, but I just want you to get the marks. So if you do struggle with the algebra, this can be really helpful for rearranging the equations, say if we needed to find current. So the bit which is times together always goes on the bottom of a triangle. So we've got Q on the top, I times T on the bottom. And if we wanted to get I, all we'd need to do is cover the I with our finger and we can see Q over T. And so that's it. So the current is equal to Q over T. So now we know that, let's remind ourselves that for electrical charge and therefore current to flow, we need to have two things. We need a closed circuit, so no breaks in it, and a source of the potential difference. Now this could be a cell, it could be a mains power pack, it could be a battery. And what we'll find is that the current is going to be the same everywhere in a single closed loop. The current that flows through a component depends on two different factors. So the resistance of the component that it's flowing through and the potential difference through that component. We need to know the relationship between potential difference, current, and resistance. So we need to know that the potential difference is equal to the current times the resistance. And again, we'll find that using the symbols can just be a quicker way to write this down. And so we might see this as V equals I times R, where V is potential difference, it's the voltage, current is the I, and R is the resistance. So potential difference is measured in volts, which is V. Current is measured in amperes or amps, which is a capital A. And resistance is measured in ohms, which is the Greek symbol omega. So again, we can use a triangle if you struggle with algebra here. Remember that the bits times together always goes on the bottom. So here we've got a V on the top and I times R on the bottom. And now you should easily be able to find whatever term you're asked to find. Now, for a given potential difference, we need to know that if we increase the resistance, we're going to decrease the current. And that's because if we increase the resistance, it's harder for that current to flow. It's a bit like making a pipe narrower. And so that means less current, less of this charge is going to be able to flow through the circuit. A bit like water flowing through a narrower pipe. In some resistors, we'll find that the resistance remains constant, even when the current increases or decreases. Now this is said to be an ohmic conductor. It obeys Ohm's law. Ohm's law tells us that the potential difference and the current are directly proportional to each other and therefore have a linear relationship. So what we'll see here is in an ohmic conductor, at a constant temperature, the resistance remains constant as the current increases. However, we'll find that the resistance of some different resistors actually changes as the current changes. So an example of this is a filament lamp. Now, filament lamps have tiny little wires within them, and the way that that lamp works is the current goes through them, they get hot and they start to glow, and that's how they illuminate the room. However, as the current increases, the filament is going to get hotter and hotter. If you imagine all of the atoms within that really hot wire, they're all going to be bouncing around the place. And what that means is that it's harder for the current to flow. Imagine trying to walk down the street and everyone's just running around the place. You're going to be knocking into people all the time. And you're not going to be able to walk as quickly. That's why as the current increases and the filament gets hotter, the resistance is going to increase. Now this doesn't obey a linear relationship. This shows a non-linear relationship. And actually the resistance increases as the current increases. Another example of a resistor whose resistance changes as the current changes is a diode. Now a diode is a very important type of component. It's one where the current only flows in one direction. And the reason for this is that the resistance in the reverse direction is very high. Now this is shown in our IV graph for the diode. We can see that in this negative direction there's actually no current flowing. However, when the current flows in the positive direction, you can see that as current increases, the potential difference increases too. And an extra thing I just want to clarify and make sure that you know. This is going to be the same graph in LED as well. Don't be afraid and think because it's not diode alone, it's going to be different. We're going to see this exact same graph for LEDs and for diodes, so make sure you learn it. Another example of a resistor whose resistance changes as current changes is an LDR. LDRs, or light-dependent resistors, are particularly interesting because their resistance is affected by the light intensity. And as the light intensity increases, the resistance decreases. Now this can make them really useful for lots of applications, such as lights which are sensitive to the dark. A good example of this is street lights. They only turn on when it starts to get dark, so perhaps they have an LDR in their circuit to ensure that this happens. The last resistor we're going to have a detailed look at here is the thermistor. Now the thermistor is very similar to an LDR in how it behaves, except instead of light intensity, they're affected by temperature. So the resistance of a thermistor is affected by the temperature. And we'll see that as temperature increases, the resistance decreases. Now again, a bit like LDRs, this makes thermistors very useful for a lot of applications. An example of a use for thermistor is a thermostat. Most people have thermostats in their homes where they set a certain temperature for their central heating to come on when it gets a bit too cold. And this thermistor would be able to enable this to happen. Now we need to know how we can build a circuit to measure the resistance of a component, such as a resistor. However, it could be something such as a bulb, thermistor, or anything really. So the two key facts that we need to know is that we need to have an ammeter in series with this component to measure its current, and we need a voltmeter in parallel to measure the potential difference. You can see what this looks like in the diagram here. A very common 6-mark question that we're likely to see in the exam will ask us to investigate the IV characteristics of a component, and they may name the component, but remember the method is going to be exactly the same regardless. The first thing that we need to say is that we need to connect a battery to the component. Then we need to add an ammeter in series. And, of course, we then need to add a voltmeter in parallel. Next up, we're going to need to add a variable resistor in series with the component. Now this is very important because we can use the variable resistor to change the potential difference. So once our circuit is all set up, and make sure in the exam you draw this circuit just like I have here, but with the relevant component in place of this resistor. We then want to record the potential difference on the voltmeter and the current on the ammeter. Once we've done that, we now want to use our variable resistor to change the potential difference. We're now going to record the new values for potential difference and current. We're going to repeat this process by changing the potential difference using the variable resistor several different times until we get enough different pieces of data. Now we're going to do something quite clever. We're going to reverse the power supplies. And this can be done by something as simple as just changing the direction of the battery. Once we do that, we're going to repeat this whole process of changing the potential difference again using the variable resistor. But this is now going to give you negative values for current because the current's going to be flowing in the opposite direction. So once we've repeated this several times, we're now going to get all of our data and we're going to plot a graph of current against potential difference. And that is going to give us one of these graphs that we've seen earlier where we have a relationship between current and voltage. When there is an electric current in a resistor, there is an energy transfer which heats the resistor. When an electrical current does work against electrical resistance, electrical energy is dissipated as thermal energy to the surroundings. This energy transfer is caused by the collisions that occur between the electrons and the ions in that lattice. We may be asked how we can reduce unwanted energy transfers in circuits. One way of doing this is to use low resistance wires. Using low resistance wires will mean that there will be fewer collisions and less energy will be wasted through heating. We might also be asked what are some advantages of the heating effect of electric currents. And simply, there's lots of appliances that use this. There's toasters, there's kettles, electric heaters. All of these rely on that heating effect of electric current to work. We need to know how to calculate the power transfer in a device, and we can relate it to the current and potential difference using this equation. Power equals potential difference times current, or P equals V times I. Again, if your math skills are a little bit dodgy, you can always use a triangle to help you rearrange this when needed. The bit with the times always goes on the bottom, so you've got P on the top and V times I on the bottom. Now remember that power is measured in watts, potential difference is measured in volts, and current is measured in amperes or amps, which is that capital A. We can also calculate the power transfer in a device using the current and the resistance. Now this equation's a little bit trickier because it's power equals current squared times resistance. Don't forget that squared. So using the symbols, that would be P equals I squared, I for current, times R. And remember, of course, power is measured in watts, which is a capital W. Current is measured in amperes or amps, which is a capital A. And resistance is measured in ohms, which is that Greek symbol of the omega sign. When charge flows in a circuit, we should know that work is done. Now we can calculate the amount of energy transferred by electrical work using the equation that energy transferred equals power times time. We can use the symbols here, E equals P times T. If we're using our standard SI units here, energy transferred will be measured in joules, which is a capital J, power is measured in watts, which is a capital W, and time will be measured in seconds, which is an S. As is the case with most equations in physics, we can write this in a triangle if you're not very confident with your math skills. To do this, we just put the P times T on the bottom. Remember, the bit with the times always goes on the bottom of a triangle, and an E on the top. Then, for whatever it is that you want to find, just cover it up with your finger and then use the triangle to get your rearranged equation. For example, power, P, equals energy over time. Here I've included a little top tip, and this applies to any equation, not just this one. We might need to convert minutes to seconds. We need to know that we do this by multiplying the minutes by 60. Alternatively, they might give you the time in hours instead. And again, in all likelihood, we're going to need to convert this into seconds. We do this by multiplying by 60 to get it into minutes, and then by 60 again. So multiplying by 3,600 converts hours to seconds so that we can use it in this equation. Now, it's not uncommon in physics, if the question's about an electrical appliance, that energy may be measured in kilowatt hours. Now, if this ever did happen, then we can use this exact same equation, however using slightly different units. The energy transferred is now measured in kilowatt hours. To be consistent with this, the power would be measured in kilowatts. And then finally, the time would be measured in hours. The amount of energy transferred can also be calculated using charge flow Q and potential difference V. Energy transferred equals charge flow times by potential difference, or using the symbols E equals Q times V. In this case, the energy transferred is measured in joules, which is a J, charge is measured in coulombs, which is a capital C, and potential difference is measured in volts, which is a capital V. If you are someone who struggles with your maths, we can just learn this triangle with the E on the top and the Q times the V on the bottom to help us with the rearranging side of this. Remember to use the triangle, cover up whatever it is that you need to find. Remember that the line means divide and the times mean times, and then you should be able to work out anything you need using that triangle if you're stuck. So mains electricity, which we have in all of our plug sockets, is an alternating current supply. Now what this means is that the current is repeatedly changing direction, and AC current is produced by an alternating potential difference. However, on the other hand, batteries that we use to put into our remote controls, for instance, or have in our phones or our laptops, they provide a direct current. Now, in a DC supply, the current flows in only one direction, and it's produced by a direct potential difference. At GCSE, we need to know a bit more information about our mains electricity supply. So, of course, we know it's an alternating current supply, or AC. However, we also need to know that it has a frequency of 50 Hz and a potential difference of 230 volts. In the United Kingdom, most of the electrical appliances are connected to the main supply using a 3-core cable. Now, this is a really safe system, so we're very lucky to have it in this country. Now, these 3 different wires in the 3-core cable are colour-coded. And this is so useful because it means we can easily identify them and keep ourselves safe. So the live wire is brown, the earth wire is made up of green and yellow stripes, and the neutral wire is blue. Now, as well as knowing the colour of these different types of wires, we also need to know the role that they play and what potential difference goes through them. So the live wire is the most dangerous wire. It carries the alternating potential difference from the main supply. So it carries a voltage of 230 volts. Now the earth wire, which is made up of green and yellow stripes, is the safety wire. And this is very important because it prevents the appliance from becoming live. Now the only time that the earth wire will ever carry a current is if there's a fault in that appliance. But again, the purpose will be to keep it safe. So the potential difference normally then going through that earth wire is 0 volts. Finally, our neutral wire that's blue in colour, this is here to complete the circuit, and this has a potential difference of 0 volts. Now let's have a look at some other key features to the plug. So we can see here that we have a fuse in this plug. Why do we have these fuses? Well, the reason for this is that if the current gets too high, a thin wire inside that fuse will melt. And the importance of this is by melting, this is going to break the circuit. Now, of course, we know that when we break the circuit, electricity is no longer flowing, and this prevents the risk of electrocution, so it makes it much safer. Now, we can also see here we have a cable grip. Now, the importance of this is it holds the wires in place. Now, we'll see that the cable grip, as well as other parts of the wire, such as the flex and the actual plastic casing, is made of the material of plastic. Now, the reason why we use plastic is because it is a good insulator. However, the wires are made up of copper and they're coated in plastic. Now, the reason why we use copper in the actual wires is because copper is a good conductor of electricity. We need to know why a live wire might be dangerous even when the switch is open. And this is a really important question because, of course, if the switch is open, you might think that the current can't flow. However, if we were to touch the live wire, we could ourselves complete the circuit. And this is because we are, of course, in contact with the ground. And so that current will flow through our bodies into the ground. And so we could be electrocuted. And that's why that live wire is always dangerous, even when the switch is open. We also need to know what the danger is of connecting the live wire to the earth wire. Now, this is a very similar answer to what we just said. If the live wire came into contact with the earth wire, the circuit would be completed, and this increases the risk of electrocution or fires. So you can see there's so many important safety rules that we need to know when using plugs. However, they are designed to keep us as safe as possible. When we have a couple of insulating materials and we rub them together, they can become electrically charged. Now, this is because electrons can move from one material to another due to friction. And what we'll see is that one material will gain electrons, just like the cloth in this diagram, and it will become negatively charged. Now, another material, though, will therefore lose electrons, just like the rod in this diagram, and that would lead to it becoming positively charged. Now, what we'll see is that the charges on these two different materials will be equal and opposite. You can see this in this diagram too. You can see that this rod has lost 6 electrons, and therefore that means that it's got 6 positive charges on it. So the charges on the materials are equal and opposite. Now, electrically charged materials will exert a force on each other when they get brought close together. Now, it's important that we know that like charges repel each other, just like these two positively charged balloons. We can observe that they will be pushed apart. However, opposite charges attract. So if one balloon was positively charged and the other was negatively charged, they would be pulled together. Now, these forces of attraction and repulsion are examples of non-contact forces, because the force is felt even without them touching each other. Now, there are lots and lots of examples of static electricity in everyday life. Very common ones are when we take off our jumpers and our hair just sticks on end. That's one example. And another is simply if you go up to your television screen, you can see there's probably a layer of dust on the front of it. And that again, that attraction of that dust to the TV screen is due to static electricity. Now, we've got these everyday examples, and most of the time it's completely safe. However, sometimes it can be dangerous and it can cause sparking. Now, a spark is caused when the build-up of charge gets so big that the electrons that have built up actually end up jumping across to become neutral again. Now, this means, due to this movement of electrons, that we have a current flowing. And this is what we see as the spark. Now, sparks can be dangerous. It depends on what is in the nearby environment. If a flammable material is nearby, then that spark could lead to an explosion. Quite a dramatic example of static charge that we've all experienced sometime is lightning. Now, we need to know what causes lightning to occur. We need to know that little ice crystals in the air are going to rub together. Now, as they bump together, there's that force of friction, which is going to cause the movement of electrons from one ice crystal to another. Now, this causes a build-up of charge in the cloud. Now, if we think relatively speaking, the ground has no charge. Whereas in those clouds, we're getting this build-up of charge. And eventually, the difference between that build-up of charge in the clouds and the no charge on the ground gets so large that the electrons will jump to the ground. And this is what lightning is. That big zigzag in the sky that we observe is actually those electrons jumping down to the ground. Another very useful example of static charge in action is a paint sprayer. And this is how things like cars would be spray painted in industry. So what we do is we hook up the paint to an electrode. Let's say here in this diagram, we've got a positive electrode for the paint. And we're going to hook up the car to the opposite charge. So here I've got a negative electrode connected to this car. So that means that the car is negatively charged. So because of this, the paint particles will all have that same positive charge. Because they all have the same charge, all of these little paint particles will repel each other, and they're going to spread out. The great thing about this is we're going to get an even coat of paint. Now we know that the car has an opposite charge to the paint. So these positively charged paint particles are going to be attracted to the car and of course repelled from each other. Now this means that we get a nice even coat of paint, and because of this attraction, even parts of the car that may not be obviously exposed to the paint will still get coated in paint due to the attraction between those positive paint particles and the negatively charged car. An electric field is a region where charged particles experience a force. All charged particles have electric fields around them. And when we see these field lines or we're asked to draw them, we need to know that field lines will always point from positive to negative. And the closer together those field lines, the stronger the field. And as a result of that, the stronger the force any charges that we put into that field will experience. Here you can see we've got a negatively charged particle, and we can see a radial field around it where all of these arrows are pointing inwards. That's because it points from positive to negative. And so because this is a negative particle, we're going to draw on our field lines pointing towards the negative. Now alternatively, if we had two parallel plates, one of which has a positive charge and the other one has a negative charge, again we're going to observe the field lines pointing from positive to negative. However, we're also going to see that these lines are straight and parallel to each other. And it's this fact, the fact that they're straight and parallel, that means that we have a uniform field. This topic starts nice and simple. We remind ourselves that magnets have north and south poles. North poles get represented by an N and south poles represented with an S. We should know that magnets will attract magnetic materials such as iron, steel, cobalt and nickel. We should know that like poles will repel and different poles attract. And of course, don't forget that magnetic forces are examples of non-contact forces. Permanent magnets produce their own magnetic field, which will always be there. Induced magnets, however, become magnetic in a magnetic field. Well, what is a magnetic field that we're talking about? Because we're going to use this concept a lot in this topic. A magnetic field is a region around a magnet where a magnetic material or another magnet will experience a force. And we represent these magnetic fields using magnetic field lines. We need to be able to draw and recognise the magnetic field pattern around a bar magnet. This diagram here shows it perfectly. So we will see that magnetic field lines will always point from north to south. This is really important. The closer the field lines, the stronger the field. And the magnetic field strength, you'll notice, certainly because they're closer together in this diagram, is at its strongest near the poles. As we move away from the magnetic field strength decreases. In the exam, we might be asked how to plot a magnetic field, and we can do this using magnetic compasses. So our first step is you're going to place the compasses around your magnet on a piece of paper. We will then mark the direction that the needle points onto the paper, and then finally we join these points together, and this will show the field lines. Magnetic compasses that we use to work out direction actually contain a small bar magnet. And when these magnetic compasses are not near to another magnet, they're actually going to line up with the magnetic field of the Earth. And this is really important because this tells us that the Earth has a magnetic core. It tells us that it's made of a material which is magnetic. Now actually the geographical south pole of the Earth is actually the magnetic north pole and vice versa. When a current flows through a conducting wire, a magnetic field gets produced around that wire. As you can see in these diagrams, they form little concentric circles around that wire. And the strength of the magnetic field that gets made depends on the size of the current going through the wire. So the bigger the current, the bigger that magnetic field, and also the distance from the wire. The closer to the wire, the stronger that magnetic field, and the further away you get, the weaker it becomes. We can also increase the strength of the magnetic field made by a wire by curling it into a solenoid, which looks just like this. The magnetic field around a solenoid actually ends up being very similar to the magnetic field around a bar magnet. The diagram here shows what that magnetic field around a solenoid looks like. You can see that inside the solenoid it is strong and uniform. We can see it's uniform because the magnetic field lines look evenly spaced. And we can also see that they're close together inside that solenoid, which is what shows that it's strong. The magnetic field is stronger inside the solenoid compared to outside because all of the small magnetic fields caused by the current in each of those turns will add up, causing a greater overall magnetic field. If we wanted to increase the strength of the magnetic field around a solenoid even more, we can add an iron core, and this makes an electromagnet. You may be asked in the exam, what are some advantages of electromagnets compared to other magnets? So one of the really important differences is that we can switch electromagnets on and off, simply by turning that current on and off. Now, you might think, why would this be useful? But if we look at the diagram here, imagine we're in some scrapyard or we're moving around old scrap cars or something. It's much easier if we can use this magnetic force, turn on the electromagnet, attract our magnetic materials and move them using that force, and then turn it off and release them. Another great advantage of electromagnets is that the strength of the electromagnet can be adjusted simply by changing the current. If we increase the current, we get a stronger electromagnet. Whereas if we have a permanent magnet, the strength of that magnet is just the strength of that magnet. We might see some applications of electromagnets come up in the exam. So let's have a look at this specific example of an electric bell and let's see how electromagnets can work. Now, looking at this, if we close the switch, we will turn on the electromagnet because the current can flow through the circuit. Now, of course, looking at the diagram, you can see we've got this iron armature. This is going to get attracted to the electromagnet, and this is going to pull the hammer towards the bell, and they're going to hit each other, and it's going to sound the bell. However, of course, when this happens, we've broken the circuit, and that turns off the electromagnet. This means that the armature is no longer attracted towards the magnet, and it's going to move back to its original position. But by moving back to its original position, it's completed the circuit again. And so we're going to have this process just go back and forth, back and forth, back and forth on repeat, sounding that bell. Now, this is one application. We could see loads of other ones too. So we just need to make sure that we can apply these principles to any little example they might give us. When we place a conductor carrying a current in a magnetic field, the magnet and that conductor will exert a force on each other. And this force causes a motion. Now, this is something that we call the motor effect, and it is a really important phenomenon. So we might ask ourselves, well, how can we increase this force acting on this wire? We could increase the size of the current in the wire or the object, or we could increase the strength of the magnetic field, and those are the two factors that we need to consider. Fleming's left-hand rule is a really handy trick that is going to help you work out the direction of any force on a current carrying wire in a magnetic field. So first things first, and I know that I was always getting this wrong myself, make sure you always pull out the right hand. You need your left hand. So as soon as you get started on this, always double check yourself. Is it my left hand? So now that you've got your left hand out, point them in the direction that you see in the diagram. So your thumb going up, pointing your forefinger, your first finger, and then your second finger sort of going to the side. But the key thing is that these all need to be at right angles to each other, okay? So don't be really lazy with it and sort of not completely point them as you see in the diagram here. So your thumb tells us the motion or the force. First finger tells us the field, and the second finger tells us the current. Now, in a question, you'd normally be given two of these and asked to find the third. So line up the two that you know about, and then the third finger or thumb is going to tell you the direction of the thing that you're being asked about. Now, really important here, they won't always tell you, oh, the current is pointing this direction. They might instead have a positive and a negative, and they expect you to know that the current flows from positive to negative. Next, let's think about the magnetic field. Again, they might not tell you the direction of the field lines. Instead, you might have a magnetic north and a magnetic south, and then you need to know that the field lines will point from north to south. So those are my top tips there. Make sure you use your left hand most of all though, because I think that is the most common mistake. A current carrying coil of wire in a magnetic field will actually rotate. So what you see here in this diagram will rotate. Now this is how electric motors work. What we would need to do is use Fleming's left-hand rule on both this side and also this side of the wire. The reason why we would want to do this is because we can work out the direction that the pink bit of the wire is pointing and that the blue bit of the wire is pointing. So if we look at this pink part first, you can see that the current is pointing in this direction here. You would need to take your second finger, which is the current finger, and point it in that direction. Then you can see the field lines aren't shown on this particular diagram, but we know that they go from north to south. So now we want to make sure that our first finger, field, is pointing in that direction. Now if we do this, we will see that our thumb is pointing upwards. And as you can see, the arrow is already here, but that's really important. Now let's do the exact same bit on the bit that I've highlighted in blue, the part of the wire nearer to the South Pole. So in this case here, let's clear some of these off. In this case here, you can see that the current is actually going in the opposite direction. It is now going away from us. So our second finger needs to point in that direction now, but the field is still pointing from north to south. So we've got our first finger pointing from north to south. Our second finger is pointing away from us and into the page. And our thumb should be pointing downwards. That tells us that we have a downward force on that part of the wire. If you didn't get those right, the main little troubleshooting tips that I would say is make sure that your fingers and thumb are all at right angles to each other. Make sure you are actually using your left hand, and make sure that you're assigning each finger and thumb the correct quantity. So remember, your thumb is your motion or your force, first finger is your field, and your second finger is current. So in this case, I can see that as it's going up here and down here, it is moving in the clockwise direction. And that will be a common question in an exam. So in an electric motor, we need to know what the role of a split ring commutator is. So split ring commutators reverse the direction of the current every half turn. The importance of this is it ensures that the coil continues to rotate in the same direction. We might also be asked, what's the role of the graphite brushes that we can see here? Well, these are of course electrical conductors. You should remember that from chemistry. And they complete the circuit as the wire rotates. However, they're not having permanent contact. Imagine if it was an actual cable that was permanently connected to this loop. And it's spinning and it's spinning and it's spinning. It's going to become a massive big old jumble, isn't it? Whereas what we have instead are these brushes which have permanent contact with the loop, but they're not having to move all the way around with the loop as it rotates. And so that makes it work perfectly. They complete the circuit as the wire rotates and makes this work. Now this equation will be a big one on calculations in this topic. So the magnetic flux density is a measure of the strength of a field. If we had a current carrying wire, which is at right angles to a magnetic field, just like we've been seeing in these motor effect questions, force exerted on it will be calculated by multiplying the magnetic flux density, which is measured in Tesla, which is capital T, times by the current, times by the length. And it's that simple. That's how we work out force on a current carrying wire in a magnetic field. We just take the magnetic flux density, times it by current, times it by length. Loudspeakers and headphones work in a similar way in that they use the motor effect to convert the variations in current in an electrical circuit into pressure variations of sound waves. So let's describe the steps as to how loudspeakers and headphones work. So, first of all, we have a coil of wire and we place it inside a permanent magnet and attach it to a diaphragm. So the current's going to flow through the coil and the wire is going to experience a force due to the motor effect because we've got this current carrying wire in the presence of a magnetic field. As a result of this, the diaphragm will move. Now, because we have an AC or alternating current here, it's changing direction the whole time. And as the AC current changes direction, the direction of the force produced by that motor effect is going to change as well. This causes the diaphragm to move back and forth, causing it to vibrate. Now, these vibrations will cause variations in the pressure of the air and will form a sound wave. And importantly here, the frequency of the sound wave produced is going to be equal to the frequency of the alternating current. We can induce the potential difference across the ends of a conductor if there is a changing magnetic field around the conductor, or if the conductor is moving relative to the magnetic field. And this can be done in one of two ways. We can move a wire in a magnetic field, or we can do the opposite. We can move a magnet in and out of a coil of wire. In both of these cases, we have this relative movement between that conductor and the magnetic field. Now, if we have a complete circuit here, then a current will be induced, and this is what we call the generator effect. Now, in the exam, it's very common for us to be asked how we can increase the size of the induced current or potential difference. So we can increase the speed of that movement, we can increase the strength of the magnetic field, or we could increase the number of turns on the coil. Another very, very common question is us being asked how we can reverse the direction of that induced current or potential difference. And in this case, we can reverse the direction of the movement of the wire or the magnet. So for instance, instead of inserting the magnet into the coil, you could remove the magnet from the coil. Or we could reverse the polarity of the magnet. So instead of putting the north in, you could put the south into that coil. And those are our two ways that we can reverse the direction of the induced current or potential difference. Make sure you know all of these facts because they are very common questions. The generator effect has different uses. It can be used as an alternator to generate an alternating current, or it can be used in a dynamo to generate a direct current. So we need to make sure that we know the difference between alternators and generators. Well, here we have an alternator. An alternator is an alternating current generator. A simple alternator is made up of a coil of wire which rotates in a magnetic field, so this could be it's placed between two magnets. Now, the ends of the coil are connected to these slip rings that we can see in this diagram. These slip rings are really important because we ensure that we have a continuous connection with the coil, and it allows the current to flow from the coil via those graphite brushes which are maintaining that connection into the circuit. And in this case, you can see that it's going to light up a lamp. Alternators get used in cars to keep the battery charged. Now this graph here shows the induced potential difference in an alternator against time for one complete cycle. You should be able to see here that the current and the potential difference change direction every half turn. You might be thinking, well, how does this tell us that? But the direction refers to whether the axis is positive or negative. So what we see here is in this first half of the cycle, it's moving in one direction, and then in the second half of the cycle, it moves in the opposite direction, and we can see that on the graph because we're in the negative y-axis. We could get asked in an exam, how can we increase that maximum potential difference? So how could we make this curve have a greater amplitude? Well, a way that we could do this is we could increase the rate of rotation, we could increase the number of turns on the coil, or we could increase the strength of the magnetic field. So make sure that you know how we could increase the maximum potential difference in an alternator. Now let us have a look at this graph in more detail, this graph of induced potential difference against time. And of course we can see that at different points of the graph, it goes up and then down and then back to zero again. Let's look at these bit by bit. So when the coil is at 0 degrees, so here, what we would observe, of course, is that the coil is moving in the same direction parallel to the direction of the magnetic field. Now no field lines will get cut then, and so no potential difference is induced. Whereas now when we have a look at when the coil is at 90 degrees, what is happening is the coil is moving at right angles to the direction of magnetic field. It's cutting it as much as possible in that case, and a maximum potential difference is induced. Next up in our rotation, we're now at 180 degrees. And again, this is still parallel to the direction of the magnetic field. No field lines are going to get interacted with, and so no potential difference is induced. Now we get to the next step, 270 degrees. At this position, the coil is moving at right angles perpendicular to the direction of the field again. So again, we've got this maximum amount of field lines being cut, and so a maximum potential difference being induced. However, it's in the opposite direction, isn't it? Whereas when it was at 90 degrees, it could be left to right. Now it might be right to left. And so we induce a potential difference which is at a maximum in the opposite direction to when it was at 90 degrees. Finally, we end up back at 360, which is essentially the exact same orientation that we had before when we were at 0 degrees. We're moving parallel to the direction of the field again, and no potential difference is induced. A dynamo is another use of the generator effect. Dynamos are direct current generators this time. Now, as you can see in this diagram, dynamos use a split ring commutator instead of those slip rings that our alternator did. Now, the importance of this split ring commutator is that it's going to make the ends of the coil swap contacts with the circuit every half turn. And the importance of this is it ensures that the current will always flow in the same direction relative to the magnetic field. And it's this that makes them generators of direct current rather than alternating current. An example of a use of dynamos is in some bicycle lamps. So as you're on your bike and you're pedalling away, the light will light up. And that is because these bicycle lamps might have a dynamo within them that generates electricity while you cycle. Now this graph here shows the induced potential difference in a dynamo against time for one complete cycle. Make sure that you can draw this and the one for alternators as well. And the main feature here is that for every one cycle, the induced potential difference varies from 0 to a maximum, back down to 0, and it does that twice. What you notice here is that the potential difference will always stay in the same direction. It never goes into negative potential differences, which is the direction of that potential difference. Always positive, which means it always stays in one direction. If we want to increase the maximum potential difference in a dynamo, we do exactly the same things that we would in an alternator. We can increase the rate of rotation. This would also squash this curve, bringing the maximums closer together. We can increase the number of turns on the coil, or we could also increase the strength of the magnetic field. So make sure you know those three and the effect it would have on your curve. Finally, let's have a look at the curve again for dynamos. Let's have a look at what's happening at each position. Now this is really similar to the one for alternators. Again, when we're at 0 degrees and the coil is in the same direction, parallel to the direction of the magnetic field, we have no potential difference induced. They're travelling in the same direction, so there's no cutting of the field lines. Whereas when we get to this maximum potential difference, the coil is at right angles to the magnetic field. And so that means that we're going to get a maximum amount of these field lines cut with this wire, and a maximum potential difference is induced. Now at 180 and 360, just like at 0, our coil moves parallel to the direction of the magnetic field, and therefore no potential difference is induced. However, when we're at 270 degrees, just the same as at 90 degrees, we're moving at right angles to the direction of the magnetic field again, and therefore we get that maximum potential difference. Notice that unlike with the alternator, we're not moving in the opposite direction, and that's because in the dynamo we had that split ring commutator which swapped the contacts every half turn. Microphones make use of the generator effect to convert the pressure variations in sound waves into variations in electrical current. So let's describe the steps as to how microphones work. First things first, we attach a coil to a diaphragm. The coil is then placed inside a permanent magnet, and the pressure variations in the sound waves cause the diaphragm, and therefore the coil it's attached to vibrate. Now that coil is now moving relative to the magnet, and this induces a potential difference in the coil. If the coil is of course part of a complete circuit, then a current can flow around that circuit. The key fact is the fact that the frequency of that induced alternating potential difference is going to be the same as the frequency of the original sound wave. Transformers are made up of two coils, a primary and a secondary coil, wound around an iron core. Now the whole job of a transformer is it can change the size of an alternating potential difference. We can scale it up or scale it down dependent on what we're using it for. So we need to be able to recognise what one of these transformers looks like we see in the diagram here, be able to label it, and also understand why we use an iron core rather than another metal. And that's because iron is magnetically soft, which means that it can be easily magnetised and demagnetized. Here we have a really important equation that we're going to use with transformers. We need to know that the ratio of the potential differences across the primary and secondary coils is dependent on the ratio of the number of turns on each coil. So here we have Vp, so the voltage or potential difference on the primary coil, divided by the potential difference on the secondary coil, is equal to the number of turns on the primary coil over the number of turns on the secondary coil. Now, the thing with this is you need to identify what belongs to the primary, what belongs to the secondary when substituting them into the equation. And my top tip for this is remember that you can write this equation upside down. So you can have Vs over Vp equals Ns over Mp. That can be really helpful when it comes to rearranging because it just simplifies it. If you have to find out what Vs is or Ns, make sure you write this upside down so that those are on the top. It's much easier to rearrange. We need to be able to recognise the difference between a step-up and a step-down transformer. Step-up transformers have more turns on the secondary coil. I imagine it literally like I'm stepping up, and so I'm going from less to having more. And when the turns increase, so does the potential difference. So the potential difference across the secondary coil is more than the potential difference across the primary coil. Step-down transformers is just the opposite. And here I think of it as, again, like I'm stepping down. The secondary coil has less turns on it than the primary coil. And therefore, as a result of that, the potential difference across the secondary coil is less than the potential difference across the primary coil. So turns and potential difference follows the same pattern. Now, if the transformers that we have are 100% efficient, which of course really doesn't generally happen, but for the sake of GCSE physics, this is what we assume. 100% efficient, the electrical power output is equal to the electrical power input. And this here is the equation that we use. So power output equals power input, but we'll use that in terms of the equation that power equals V times I. And we say that Vs times Is equals Vp times Ip. And this of course means that the potential difference of the secondary coil times by the current in the secondary coil is equal to the potential difference in the primary coil times by the current in the primary coil. So we've seen all the maths there, but now we need to have a look at how transformers work. We need to be able to describe all of the steps as to how transformers work. So, first step, primary voltage supplies an alternating current to the primary coil. Next, this alternating current induces an alternating magnetic field in the iron core. So the current never flows in that iron core. Instead, that magnetic field that we just induced is what's able to move through it. And of course, as it's moving through that core, it moves from where the primary coil is to where the secondary coil is. And that alternating magnetic field induces an alternating potential difference in the secondary coil. Now that we've got this induced potential difference, that produces an alternating current. And so those are 4 key steps that we need to know to describe how transformers work. As a final little reminder here and a top tip, don't forget that transformers will only work with an alternating current. If we connected them to a direct current like a battery, they would not work. We need that alternating current of a main supply. The national grid is a system of cables and transformers linking power stations to homes and factories to transfer electrical power. We're going to find 2 different types of transformer within the national grid. We're going to find step-up transformers and step-down transformers. Step-up transformers are found between power stations and transmission cables. Step-up transformers are really important. They're designed to increase the potential difference and therefore decrease the current. Now this ensures less energy gets lost through the heating of those cables. This increases efficiency. So more of that electrical energy is transferred from those power stations to the homes and the factories they're going to. Now step-down transformers, on the other hand, are found between transmission cables and homes and factories. Now, step-down transformers decrease the potential difference to a lower and a safer value. It would be incredibly dangerous if we had potential differences as high as they were due to that step-up transformer entering our homes. The risk of electric shocks and fires would be very, very high. So we use step-down transformers, decrease that potential difference, and reduce those risks. Density is a measurement of how much stuff there is within an object. And we can calculate the density using the equation that density equals mass over volume. Now, if we want to use the symbol equation for this, we need to know that density is represented by the Greek symbol rho. Now, rho looks a bit like a curly P. So we can say that rho equals m over v. We need to know that density is generally measured in kilograms per metre cubed, mass is measured in kilograms, and volume is measured in metres cubed. Now, to be able to calculate density in the exam, we're often going to be asked to calculate the volume of different shapes. So we need to make sure that we can work out the volumes of cubes, spheres, cylinders, and cones. Let's remind ourselves of how we calculate these volumes and make sure you learn these formulas. So if we have a cube like we have here, we could use a ruler to measure the length of one of its sides, and we can calculate the volume by taking that length, x, and cubing it. So the volume of a cube is x cubed. A cylinder, on the other hand, we need to know both its height and its diameter. Its height we can use a ruler to measure, and the diameter we may use vernier calipers. Formula here is going to be pi times by d over 2 squared times by h. Or we may remember that from maths as pi r squared h, because of course the radius is a half of the diameter. If we had a sphere, we would take those vernier calipers again and use it to work out the diameter of the sphere. Then the volume would be calculated using 4/3 pi times by d over 2 cubed. Finally, we've got the volume of a cone. So here again, we need two dimensions. We need its height from its peak up to its base, and we need its diameter. So to calculate the volume of a cone, the calculation is 1/3 times by pi times by d over 2 squared times by the height. The particle model can be used to explain the different states of matter. So if we look at a solid, for example, we can see that its particles are arranged in a regular pattern, they're very close together, and they vibrate about fixed positions. Now, because they're very close together, solids are actually very dense. Now let's look at liquids. So liquids are found in a random arrangement this time. Particles are still close together, but the particles move around each other. Now, because these particles are still close, just not very close, they are still really quite dense. However, when we compare that to a gas, where the particles are still randomly arranged, but they're far apart now, moving quickly in all directions, it's the fact that they're far apart and therefore occupy a much larger volume that means that they have really quite a low density. In the exam, we need to be able to describe an experiment to find the density of an irregularly shaped object. So this could be something like a stone, something that isn't a distinctive shape, which you have a formula to work out its volume for. So here we need to know this method. We'd start off by measuring the mass of the object using our standard top pan balance. And then we're going to get a displacement can like the one in the diagram. And we're going to fill it with water until the water is level with the bottom of that pipe, just as we can see here. We're then going to place an empty measuring cylinder under the pipe. Now we're going to be really careful here and we're going to drop our irregularly shaped object into the water. Now you can see in this example here, we've wrapped some string around the stone so that we can lower it in slowly. And the reason why this is so important is if we just dropped it in, then water would likely splash everywhere and we would lose some water, which would distort our results. So we'll place it in, and then we're going to see water pour out of this tube. We're going to wait until the water stops leaving the displacement can, And then we're going to have a look at our cylinder, which was catching all of that displaced water, and we're going to measure the volume of that displaced water. Now that volume is the same as the volume of your object. So here then, we can use the equation for density, which is density equals mass divided by the volume, to calculate the density of that object. We could also be asked to describe an experiment to find the density of a regularly shaped object, such as a cube or something. And here the method is a little bit simpler in a way. First off, we're going to measure the dimensions of the shape. So we're going to use rulers to measure any lengths and vernier calipers to find diameters. We're then going to measure the mass of the object using a top-pan balance. And then we're going to calculate the volume of the shape using those dimensions that we found. So here, if we had this cube, we'd measure the dimension of its length and we're going to cube it to get that volume. Then, now that we've got the mass and the volume, we're going to use the equation for density to calculate the density of the object. So in this case, we'd say density equals mass divided by that volume. We need to consider some potential errors that might arise when we find an object's density. Firstly, let us consider that different top-pan balances being used by different people may have different calibrations. This could result in an error in measuring the mass. Also, we need to consider that different measuring cylinders might have different resolutions. One measuring cylinder might measure things to the smallest 1 centimetre cubed, another might just measure it to the nearest 5 centimetre cubed. That's the difference in resolution, and this could lead to different students getting different answers for those volumes. Finally, we can consider an incorrect setup of the displacement can. Maybe they didn't add water right to the very bottom of that tube, and therefore we might get different readings for the volumes because some people may have errors in their readings. Finally, we need to know that when talking about density, we might be given measurements for density in terms of grams per centimetre cubed, but we actually need it in kilograms per metres cubed, or vice versa. So it's useful to know the conversion between the two. So if we have a measurement in grams per centimetre cubed and we want to convert it to kilograms per metres cubed, we simply need to multiply through by 1000. Conversely, if we have a density in kilograms per metres cubed and we want to get it in grams per centimetre cubed, all we need to do is divide by 1000. During changes in states, mass is conserved. We need to know that changes of states are actually physical changes, they're not chemical changes. If we reverse the process, the material will regain its original properties. So if we think of some of these processes that take place, we should know that going from a solid to a liquid is the process of melting, whereas going from a liquid to a solid is freezing. So as we go back and forth there and we reverse those processes of melting and freezing, the material will regain its original properties. Likewise, when we go from a liquid to a gas, that's the process of boiling, whereas going from a gas to a liquid is condensing. Now, the final process that we need to know, one that we're probably less familiar with, is the process of sublimation. Sublimation is the process where the state changes from a solid all the way to a gas. And although we don't have quite as much experience of this, I'm sure that you can visualise opening a really cold freezer and it looks like steam is coming off of the ice. Now this is the process of sublimation. That solid ice is changing to a gas. Internal energy is the energy stored inside a system by the particles that make up that system. So this means that it's equal to the sum all of the kinetic and potential energies of all of the particles that make up that system. If we have a material and that material gets heated or cooled, the material would change in one of two ways. The first change is that that material might change temperature. And this means that there's a change in the thermal energy store of the material. So if you've heated up this material, it will increase in temperature because it has gained the thermal energy store. The second change that we might see is that chemical bonds may form or they may break between the particles. This means that there's a change in the chemical potential energy store of the material. If a material or a system sees a change in its temperature, the scale of that temperature change, it depends on one of three factors. Firstly, you've got the type of the material. Secondly, the amount of energy that's been put into the system. Finally, we've got the mass of the material. The reason why the type of material affects the scale of that temperature change is because different materials have different specific heat capacities. Now, it's really important we know the definition for specific heat capacity. Specific heat capacity is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree C. We need to know this equation, which enables us to find the change in thermal energy of a system. So, the change in thermal energy is equal to the mass times by that specific heat capacity of the material times by the temperature change of the system. As always, we might find it easier to use the symbols for this. Here, though, we're going to see a triangle, which is known as the Greek symbol delta. So we've got delta E equals m times c, that's specific heat capacity, times by delta theta. Now in this case, those triangles or the deltas refer to the change of a substance. So we've got the change in energy, and delta theta is the change in temperature. So we also need to know the change in thermal energy is measured in joules, mass is measured in kilograms, specific heat capacity is measured in joules per kilogram per degree Celsius, and finally the temperature change is measured in degrees C. When a substance changes state, we'll see that the temperature doesn't actually change during this process. However, the stored energy within that substance, and therefore its internal energy, does change. So this is where we're introduced to a term, which is the specific latent heat. And we need to know that the specific latent heat is the energy required to change the state of 1 kilogram of a substance without changing its temperature. So we've got two different variations of specific latent heat. We've got specific latent heat of vaporization and specific latent heat of fusion. So specific latent heat of vaporization involves changing the state between liquid and vapor. I like to think vaporization, the vapor's in there somewhere, the gas, okay? So that could be going from liquid to vapor or vapor to liquid. We will still refer to this as the specific latent heat of vaporization. Then we've got specific latent heat of fusion, which this time is the energy required to change the state from solid to liquid of 1 kilogram of a substance. So again, specific latent heat of fusion could be talked about either going from solid to liquid or liquid to solid. It will be the same. We need to be able to calculate the energy required to change the state of material. So we need to know this equation. The energy for a change in state is equal to mass times by the specific latent heat. So the formula for this is delta E, remember delta means change, which equals m times L. The energy for a change of state is measured in joules, mass is still measured in kilograms, and specific latent heat is measured in joules per kilogram. In the exam, it's very common that we'll be asked to interpret heating and cooling curves. Let's take a look at this curve as an example. So here we can see that we've got this region here where we're at negative temperature, so it's very cold, and we can see that we have a solid. As we put energy in, we're going to see that this solid gets warmer and warmer and warmer until eventually it stops getting warmer and it stays flat on this curve for a period. Now the flat regions, these horizontal regions, are where we have changes in state. And so here in this case, we're going to go from a solid to a liquid. And all of that energy is going into breaking the bonds. Nothing is going towards increasing the thermal energy store. So then we go on. We've broken all of those bonds, and now we have a liquid whose temperature is increasing, until eventually it reaches another point. it reaches the boiling point of the substance. And this is where again it now goes flat and it remains horizontal for a while. And that's because all of the bonds within that liquid are going to be broken apart and it's going to now become a gas or a vapour. Now, when we put more energy in, what's going to happen is the gas is going to increase in thermal energy and therefore its temperature is going to increase. Now, this particular curve is looking at water. I know that because I can see that it has a melting or freezing point of 0 degrees and it has a boiling point at 100 degrees. So it's important that we know that water boils at 100 degrees and it melts at 0 degrees. And this is actually the only material whose melting and boiling point they expect you to know. Just water, but luckily we've got everyday experience of that, so I'm sure you're familiar with those facts already. In a gas, the molecules are constantly moving around in random directions. The temperature of a gas is related to the average kinetic energy of its molecules. And therefore, the higher the average kinetic energy of that gas, so the faster those molecules are moving, the higher its temperature. And this is why heating a gas, and so giving it more energy, leads to an increase in its temperature. If we had a gas in a sealed container, and so its volume is constant, and we increased the temperature of the gas, we would see that the pressure increases. Let's think about why. The particles are going to have more kinetic energy, and therefore they're going to be moving around the container more quickly. Now, if it's moving more quickly, the particles are going to collide with the walls of that container more frequently. This means that we're going to exert a greater total force on the walls of that container. Now, this increases the pressure. Now, temperature and pressure are directly proportional. If we increase the temperature by a certain amount, pressure will also increase by that same amount. So say if we doubled the temperature, the pressure would also double. We need to know how to convert between the Kelvin and the Celsius temperature scales. If we have the temperature in Celsius, we need to add 273 to get the temperature in Kelvin. Now, Kelvin is sometimes referred to as the absolute scale of temperature. 0 Kelvin is equal to minus 273 degrees C. And this temperature is very special because we refer to this as absolute zero. And at absolute zero, the average kinetic energy of all of the particles is 0, and the particles have stopped moving. It's important that we know that gases exert a pressure on the walls of a container. The reason for this is that the gas particles collide with the walls of the container, exerting a force. And so the pressure produces a net force at right angles to the walls of the container or the surface. And pressure changes can actually cause a gas to be compressed or expanded. If we were to increase the volume of a container at a constant temperature, we're going to see that the pressure decreases. Let's have a think about why increasing the volume at a constant temperature will decrease the pressure. Let's have a look at our diagrams to help us out here. We can see that when we have the bigger volume, so V1, the distance that the particles can move between the collisions has been increased because there's more space for them to move around. This will mean that there are less frequent collisions between the particles and the walls of the container. So this means there will be a smaller total force and therefore a smaller pressure. We can actually calculate the change in the pressure or the volume of a gas using the following equation. So it's quite an unusual one. Here we have pressure times volume equals constant. That means that if you have a certain system, the pressure times the volume will be the same regardless, so long as all the other conditions stay the same. So long as the temperature stays the same, so long as no more gas is added or anything. And if we have a system where we change the volume or we change the pressure, it can be helpful to use it in this format, where we say P1 times V1, so the pressure and volume initially, is equal to P2 times V2, the pressure and volume after a change. We can see here that pressure is inversely proportional to volume at constant temperature, and therefore as the pressure increases, the volume decreases. Work is the transfer of energy by a force. So when work is done on a gas, the internal energy will increase, and this can lead to the temperature of the gas increasing. So we need to be able to explain for the exam why compressing a gas, such as using a bicycle pump, can cause the temperature of the gas to increase. So these are your steps. We need to know that a force is applied on the gas to compress it. This results in work being done on the gas due to the fact that we know that work done equals force times by distance. Now, the energy that the gas gains is not transferred to the surroundings fast enough. It's happened too quickly. So this leads to the gas increasing in temperature.
Ouch! This is why in some videos I'll explain scratches.